So before we talk more about gravitation specifically, I want to take some time to just talk about how scientists conceive of the universe and how it works. And scientists identify four forces as being fundamental, meaning that all forces are based on these in some way. The first is gravitation, that we're going to be talking about more specifically. Then we also have the electromagnetic force, which you've heard of. It encompasses both the attraction and repulsion between charged objects, like electrons, two electrons would repel each other, or a proton and an electron would attract each other, that sort of thing. It also encompasses the magnetic force, which is, something you stick to your refrigerator, those magnets, the forces there. Then the other two fundamental forces are maybe ones that you haven't heard of unless you've read more about physics. They're the weak force and the strong force. The weak force is very difficult to find out any useful information about. If you look it up, you'll find things that say the weak force has something to do with radioactive decay, and then you'll find some things that have really complicated math equations. There really isn't anything in the middle. So what I know about the weak force is that it's involved in radioactive decay. You can try to search more on your own if you're interested. And then the strong force is the force that holds nuclei together. There's an attractive force that exists between protons with each other and protons with neutrons. And this is why the nuclei of atoms, which are have a bunch of protons, don't just fly apart because there's an electric repulsion, but the strong force attracts and it's stronger. That's the name. And these forces are important on different scales, and they have different levels of strength. So on the scale of large objects to small objects, this is how things go. Gravity is more important than these others on the macroscopic scale. Generally, electromagnetic becomes important down at the molecular and atomic level. Weak is slightly below the atomic level, because it has to do with radioactive decay. So it's within sort of bigger atoms, and then the strong force is within nuclei. So it has to do with the subatomic scale. And in terms of the relative strength of these forces, this is in order from weakest to strongest. A theory called quantum electrodynamics has successfully been able to unite these three forces under a single framework. But gravitation, we don't really have more of an explanation for, and we haven't figured out a way to connect it to the other ones. String theory, or M theory, they're different names for the same thing. String theory is more popularized, but M theory is what a scientist would be more likely to call it. As well as something called quantum loop gravity, are attempts to put all four of these together in the same framework, which so far nobody has been able to do. So those are the forces, and one of the goals that physicists have been trying at is to come up with some theory that incorporates all four of them in a way that's accurate and accurate to reality and logically consistent. Anyway, as I said, we're going to be looking at gravitation right here. So Newton formulated this law of universal gravitation. Universal means, for everything. So this law applies to any two particles in the universe or objects. Any two objects will attract each other gravitationally. So if anyone ever tells you you're not attractive, you can say, yes, I am. Isaac Newton said so. The formula for that, it looks like this. Got a big G, m1, m2 over r squared. So m1, m2 are the two masses involved. So the bigger the mass, the bigger the attraction. The smaller the mass, the lesser the attractive force. And then r is the distance between their centers. That's important because it is the distance from the center. So if we wanted to find the magnitude of force the Earth exerts on something, you'd have to go from the center of the Earth, not from the surface of the Earth. G is a constant 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Yeah. So this is the law of universal gravitation. I'm not putting a box around it because we're primarily going to be dealing with something on the surface, things on the surface of the Earth, for which we're going to use a simpler formula. But this applies when you get out farther from the surface of the Earth and you're dealing with planetary orbits and stuff like that, which we will do later on in the course. But just as an exercise, we can calculate the magnitude of the gravitational force the Earth exerts on me. So let's say this is the mass of the Earth, this is the mass of Parkhurst, and I'm a distance of about that far from the center of the Earth. So we can calculate G times mass 1, 5.98 times 10 to the 24th, times mass 2, 85, over 6.38 times 10 to the 6th squared. And we can get a value for that. So let's see, 6.67. If you don't know, on your calculator there's this button that says E, double E. It's above the comma on the 84 series. The second E, that means times 10 to the power of. So 6.67 E minus 11 means 6.67 times 10 to the minus 11th. Then we have times 5.98, whoops, 5.98, I can't type, 0.98, there we go, times 10 to the 24th, times 85, divided by 6.38 E6 squared. And we get about, with sig figs, 830 newtons. So that would be the magnitude of the gravitational force the Earth exerts on me. Now this would have been more fun in class time, but because we pick an actual person. But let's say Bob. Let's say we have a man named Bob who is of similar mass to me, maybe a little bit smaller, and we'll say he's 2 meters away from me. Well, then the gravitational force Bob exerts on me and just plug those numbers into the equation, and we would get about 1.1 times 10 to the minus 7th newtons. So what's the difference? That is the difference. If you multiply the gravitational force Bob exerts on me by this number, you get the gravitational force the Earth exerts on me. Comparatively, these two, this is super small compared to this. Why don't we feel pulled toward one another? Well, the gravitational force from Earth is much, much stronger than the force from another person. Yeah, so even though you can say that you are attractive, the gravitational force, your attractiveness is actually negligible. I'm sorry. So we pretty much only deal with the gravitational force the Earth exerts on somebody. Now, commonly used terms, mass and weight. Now, mass we've already established. Mass is the amount of matter in an object. Mass has units of kilograms. Weight, however, is not the same as mass. Weight, in fact, is the same thing as gravitational force. Okay, the units for that, it is a force, so the units would be newtons. So a lot of people in the world will lie when you ask what their weight is, and not just because they don't want you to know how fat they are. They'll accidentally lie because they'll tell you something in kilograms. So what they're telling you is actually your mass and not their weight. So where would my weight be greater here on the moon? Well, on Earth, because gravitational force is less on the moon because the moon is less massive. Where would my mass be greater here on the moon? Well, there's no difference. The amount of matter I have doesn't change based on location, while gravitational force does. So that's something. Weight changes based on location. If I go up to the top of a tall mountain, my weight will be slightly less, maybe negligibly less, but slightly less than it is where I am right now. If I go down to sea level, my weight would increase somewhat. If I go out to the space station, my weight would decrease, but no matter where I am, my mass will be the same. So if I wanted to change my mass, I'd need to, exercise and eat healthily and stuff like that. But to change my weight, I could just go to a new location. Yeah. So anyway, going back to calculation from number 12, I got 830 newtons for that, right? What happens if I divide this force by my mass? Well, it's 830 newtons divided by 85 kilograms. What do I get from that? 9.8 meters per second squared. How about that? That looks familiar, right? That's just G. Well, it turns out G comes from Newton's law of universal gravitation. If we look at this formula, little g is actually big G times the mass of Earth divided by radius of Earth squared. So that's where little g comes from. It's the gravitational acceleration near the surface of the Earth. So on Earth, we can say force from gravitation is just m times g. And this is what we will be using now. So I gave you the big nasty law of gravitation equation, just so you know, and understand the concept, but we won't be using this equation to calculate stuff until later on in the year when we do planetary orbits. As long as we're near the surface of the Earth, we're going to use mg. The acceleration due to gravity at any point is just gm over r squared. It's just an example if I have involving more than one force. A piece of paper of mass 2.5 grams is dropped and experiences an upward force of air resistance equal to that. What's its acceleration? Well, this piece of paper is dropped. It has an upward force of air resistance. It has a downward force of gravitation. And we know that the gravitational force is equal to mg. So applying Newton's second law, we can say we have air resistance acting upward, gravitational force acting downward, and from there we can calculate the acceleration. Air resistance 1.4 times 10 to the minus 2. Mass is 2.5 grams, which is 0.0025 kilograms, times 9.8. It's 0.0025 times acceleration. We can use that to calculate the acceleration. It's a negative 4.2. Well, I've called this air resistance force upward force positive, the gravitational force negative, so negative 4.2, which means that it is 4.2 meters per second squared downward. Right, so that's just a simple problem. You'll have some like this on the homework, some things where you just have to take m times g. Very simple. We'll get into some more complicated stuff next time.